Okay, we are going to use the method of Laplace transforms to solve a differential equation. I've actually given us an initial value problem here. So I've got y prime plus 5y is e to the negative t plus 2, y of 0 is equal to 1. Okay. Now, we do not need Laplace transforms to solve this. This is a first order linear differential equation. I've got two perfectly good methods of finding out what the answer is. I can use the method of integrating factors. I can use guess and check. And if I want to sound more sophisticated about guess and check, I can call it the method of undetermined coefficients. Okay. Either of those would work. Okay. So I'm not trying to convince you here that Laplace transforms is the best method for this particular problem. Honestly, I don't think it is. Okay. But Laplace transforms is the best method for certain types of problems that are a little bit more difficult. So I want to just see how Laplace transforms work and get used to working with them with something that's not too taxing. Okay. Now, I've also written up here the two main formulas that I'm going to use. Okay. So formula number 1 and formula number 11. Now, because my whiteboard is finite, okay, I'm not always going to use the space to write down the formulas that I need. I'm sometimes just going to refer to them by number and say, I'm going to use formula 14 now. Okay. So I recommend that going forward, every time you're working on differential equations in Chapter 6, you have that handout with you, that formula sheet. So that as you're watching the videos, if I say we're going to use formula 1, you know we're using this formula. Okay. As you're doing the homework, you can look up the formulas. Quizzes. Showing your work, a good idea is to write down the formula number. Okay. Now, if you use the formulas correctly, I should be able to tell exactly what formula you're using. If you use the formulas incorrectly, I can tell you from past experience, I can't always read your mind and see what you were trying to do. So this is a way of making my life a little bit easier and making your life a little bit better, because if I can follow your train of thought, you're more likely to get some partial credit. So it's just sort of a safety net. Okay. I am also going to use the fact that the Laplace transform and the inverse Laplace transform are linear. Those we're going to use so often, I'm not going to bother to refer to them by number. But all the other formulas I'm going to refer to by number whenever I use them. Okay. So here's the basic idea. Here's my differential equation. I'm going to take the Laplace transform of both sides. So I'm going to say the Laplace transform of y prime plus 5y. Well, that's equal to the Laplace transform of e to the negative t plus 2. And then Laplace transforms are linear. So I can distribute this across a sum, and I can pull out any constants. Ordinarily, I'll probably do that in just one step. Since this is our first time, I'm going to do it in two. So I can say this is the Laplace transform of y prime plus the Laplace transform of 5y. And that's equal to the Laplace transform of e to the negative t plus the Laplace transform of 2. Okay. And this 2 is kind of interesting. You might be thinking, oh, I don't think she's told us what to do with constants yet. But I have, because 2 is the same thing as 2 copies of e to the 0 times t. It's a really cheap trick, but you gotta know it and you gotta use it every time you've got a constant. Rewrite that constant as that constant times e to the 0t, and then you've got an e to the at where your a is just 0. Okay, so now I'm going to go through and I'm going to pull out any constants. So this is the Laplace transform of y prime plus 5 times the Laplace transform of y. And that's equal to the Laplace transform of e to the negative t. Here there was no constant to pull out. But here I can say this is 2 times the Laplace transform of e to the 0t. Okay. As I said, usually going forward, I'll go from this line straight to this line. So I'll distribute the Laplace transform across addition and subtraction and just factor any constants out. Okay. All right, now we're ready to use some rules. So for the Laplace transform of y prime, rule number 11 told us what to do there. That's going to give me s copies of the Laplace transform of y minus my y value at 0. And since I gave us that, I can say this is minus 1. So that right there is just rule number 11, plus 5 copies of the Laplace transform of y. And that's equal to, now here, I'm going to be using rule 1. That's just an exponential. That's e to the at, where my a would be negative 1. So that's going to give me 1 over s minus a is minus a negative 1. So that's going to become plus 1. Plus 2 copies of, this is going to be 1 over s minus 0, which is just 1 over s. All right, excellent. So now I've got this equation. Notice there's no calculus in here. This is an algebraic equation in my unknown function. My unknown function is the Laplace transform of y. If I wanted to, just to remind you, I could call that capital Y of s. That's going to be some function of s. I think for this problem I'm just going to keep writing it as the Laplace transform of y, but I've got some options for the notation. Okay. And I don't have any derivatives or any integrals in this equation. I've just got that unknown function times s minus 1, plus that unknown function times 5 equals this other function of s. That's just algebra. So I'm going to now solve this algebra equation for the Laplace transform of y. So over here on the left, I can actually just factor out the Laplace transform of y from this term and this term. I can say that's being multiplied by s plus 5, and then I'm still also subtracting 1. Okay. And that's equal to 1 over s plus 1 plus 2 over s. Well, to solve for the Laplace transform of y, all I need to do now is just divide by s plus 5. So this is going to mean that the Laplace transform of y is going to equal 1 over s plus 5 times s plus 1 plus, oh, I'm sorry, I have to do two things. I forgot about that minus 1 there. I'm so sorry. I just didn't see that for a second. This means the Laplace transform of y times s plus 5 is equal to 1 over s plus 1 plus 2 over s plus 1. I need to add over that 1 first. Now I can divide by s plus 5. I'll just come up here. The Laplace transform of y is going to be 1 over s plus 5 times s plus 1 plus 2 over s plus 5 times s plus 1 over s plus 5. So we were able to solve this algebra problem for our unknown function of s, the Laplace transform of y. Okay. What I want to be able to do now is apply the inverse Laplace transform to get back to the original unknown function y of t that showed up in my differential equation. Now, if I take a look, I like that term, because that term looks like that. That's just this formula with a equaling negative 5. So if I apply the inverse Laplace transform to this piece, I'm going to get e to the negative 5t. That's just using rule 1 to go from here backwards. Okay. So I like that piece. Not so crazy about these two pieces. And if you look on the table of Laplace transforms, there's nothing there that's particularly helpful except for this one. Okay. What I need to do is use partial fractions to write these fractions, which have a kind of complicated denominator, as a sum of smaller fractions that have a much simpler denominator that are going to match that formula. Okay. So that's where we will pick up in the next video.